Hello. NCERT Board Questions MCQ. A particle is dropped from a height h. The de-Broglie wavelength of the particle as a function of height is proportional to. We know de-Broglie wavelength is given by h upon mv, where v is the velocity, m is the mass, h is Planck constant. In this question, body of mass m dropping from height h means initial velocity 0. We have to find the final velocity after dropping of height h. So, using the third equation, v square is equal to u square plus 2gh, and v will be root of 2gh. Putting the value of v in equation 1, we get lambda equal to h upon mv, 2gh root of it. Now h, m and g are constant, then lambda will be directly proportional to 1 upon root h, inversely proportional to root h, or h to the power minus half. So here option 4 is correct. In the question 2, the threshold frequency of a certain metal is given 3.3 into 10 to the power 14 Hz. If the light of frequency 8.2 into 10 to the power 14 Hz is incident on the metal, then cutoff voltage for the photoelectric emission you have to find. So here threshold frequency nu naught is 3.3 into 10 to the power 14 Hz, and frequency incidenting is 8.2 into 10 to the power 14 Hz. We have to find out the cutoff voltage. Using the photoelectric equation, h nu equal to h nu naught plus EV naught. So here EV naught will be equal to h nu minus h nu naught, or V naught will be the stopping voltage. It's given by h nu minus nu naught upon E. We put all the values 6.62 into 10 to the power minus 34 into, you can see 8.2 minus 3.3 after taking 10 to the power 14 common, and charge of electron 1.6 into 10 to the power minus 19. After solving, it comes 2 volts. So option 1 is correct. Monochromatic light of frequency 6 into 10 to the power 14 Hz is produced by a laser. 6 into 10 to the power 14. The power emitted is 2 into 10 to the power minus 3 watt. We have to find the number of photons emitted per second. Power equal to n h nu. H nu is the energy of one photon. N is the number of photons emitted from the source per second. So number of photons per second. We have to find out n. So n will be power p divided by h nu. Power is given here 2 into 10 to the power minus 3 watt upon h, Planck constant 6.63, 10 to the power minus 14, 34 into nu, frequency 6 into 10 to the power 14. If we solve it, comes here 5 into 10 to the power 15 photons per second. So option 4 is correct. In this question, wavelength of the photon is needed to remove a proton from the nucleus, which is bound to the nucleus by 1 million electron volt energy. We know energy equal to the binding energy. Energy is given by H by lambda. Energy is 1 million electron volt. So we have to find out the wavelength. Lambda equal to E upon Hc. Here E energy 1 million. So 1 into 10 to the power is 1.6, 10 to the power minus 13, because in million electron volt converting H 6.63 10 to the power minus 34 and C 3 into 10 to the power 8 per second. After solving, comes here 12.43 into 10 to the power minus 13 or 1.243 into 10 to the power minus 3 nanometer. So here option 2 is correct. A proton and alpha particle are accelerated to the same potential. The ratio de-Broglie wavelength of proton and alpha particle we have to find. In this question, we know de-Broglie wavelength lambda equal to h upon mv or h upon p. We know p equal to root of 2me is the energy. So P will be 2mqv, where capital V is the voltage difference. This is the voltage difference or potential difference. Now put in this equation 1, lambda will be h upon 2mqv. This question, if F, H and V potential difference same, then if V is constant, then lambda is inversely proportional to root of mq. Now we have to find lambda for proton, lambda for alpha particle inversely. So m of alpha particle, q of alpha particle upon m of proton, q of proton, root of it. Now we know mass of alpha particle is 4 times mass of proton and charge of alpha particle is 2 times charge of proton. So if we cancel out mp and qp, it will be root 8 to 1. This is the ratio. So option 4 is correct. Hello. In this question, considering a beam of electrons, each electron with energy E0 incident on a metal surface kept in evacuated chamber, then here electron can be emitted with any energy with a maximum of E0. Means, say, this is the equation, Einstein equation, work function plus kinetic energy. Here, in this equation, kinetic energy is maximum. It means with the same photon of energy h nu, kinetic energy of the photoelectrons emitted from between say 0 to maximum kinetic energy. Any value between 0 to maximum. So, hello. In this question, de-Broglie wavelength of a particle of kinetic energy k is lambda. What will be the wavelength of the particle if kinetic energy is k by 4? Now we know de-Broglie wavelength is given by h upon p. P is called linear momentum or 2me. M is the mass of the particle and E is the energy, kinetic energy of the particle. If m is constant, then lambda inversely proportional to root of E. So here lambda 2 upon lambda 1, the ratio will be E1 upon E2. If energy initially here is K and finally is K by 4, so here it will be root of 4 or 2. The final wavelength will be 2 times of the initial is lambda. So here This is the wavelength emitted with 2 lambda. Option 2 is correct. In an accelerator experiment on high energy collisions of electrons with positrons, a certain event is interpreted as annihilation of the electron-positron pair of total energy 10.2 in 10 power 9 electron volt and 2 gamma ray photons of equal energy emitted. The wavelength associated with gamma ray, each gamma ray is. So we have to find out the wavelength. Now energy, we know the energy equal to hc by lambda, or lambda will be hc upon E. Putting the values here, h is Planck constant 6.63 into 10 power minus 34. C is the velocity of light 3 into 10 power 8 upon E is the energy 10.2 into 10 power 9 electron volt. If convert into joule, will become 1.6 in 10 power minus 19. But here, this is the energy of both the electrons and positron and 2 gamma ray photons. So here for each gamma ray photon, wavelength will be, so we divide it by 2, will be half. If we solve it, lambda will come here 2.4375 into 10 power minus 16 meter, or 2.44 into 10 power minus 16 here. This is the wavelength of the each gamma ray photon. So here option 3 is correct. In this question, threshold wavelength of photoelectric emission from a material is 5200 angstrom. Now, from which material and what radiations are coming out from the same material? Here, this is very tricky question. We must know the radiations of visible light. Visible is spectrum from, say, VIBGYOR, violet to red color, roughly 4000 angstrom to 7600 angstrom. And for, say, ultraviolet rays, UV rays, this wavelength is varying from 100 angstrom to 4000 angstrom. And for infrared rays, this wavelength comes in between 7000 angstrom to roughly 10,000 angstrom. By using photoelectric equation, hc by lambda equal to hc by lambda naught plus kinetic energy. Here is the wavelength threshold given 5200 angstrom. If wavelength is less than this energy of photon is more than the work function, then and only then electrons, photoelectrons emitted and kinetic energy exists. If the energy is less than the work function, no electron emitted, means lambda should be less than this value, means here ultraviolet rays is needed to emit the electron from the metal surface. So here 1 watt ultraviolet rays is the option 3 is correct. Hello, in this question, if velocity of electron increases the de-Broglie wavelength, so we know the relation for de-Broglie wavelength given by h upon mv. H and m are constant for electron, means lambda is inversely proportional to v. If velocity decreases, then lambda must decrease and vice versa. So option 2 is correct. In this question, a blue lamp mainly emits light of wavelength 4500 angstrom. The lamp is rated 150 watt and here 8% of the energy emitted as visible light. We have to find out the number of photons emitted per second. So here power equal to N is the number of photons per second into h nu or hc by lambda. It means N can be found P lambda upon hc. Putting all the values here, P means 150 watt, but only 8% energy is utilized here because of the efficiency. Lambda is 4500 angstrom, converting into meter 10 power minus 10. 1 angstrom में 10 power minus 10 मीटर होता है. H 6.63 10 power minus 34 into C, speed of light. We solve it. It comes roughly 2.719 in 10 power 19 photon per second, approximately 3 into 10 power 19 photons per second. So option 1 is correct. In this question, photoelectric cell is illuminated by a point source of light at 1 meter distance away. The plate emits electrons having a stopping voltage V. Then we have to find stopping voltage. We know stopping voltage depends on frequency of the incidenting photons but not on intensity. Similarly, intensity depends and this current depends on intensity and not on frequency. So here is stopping voltage. If we changing the distance of source from the plate by changing the distance r from the source to the plate, intensity changes. Intensity is inversely proportional to square of the distance. But we not stopping voltage depends on frequency, not on intensity. It means stopping voltage remains the same. It is not depending on the distance, so it will remain the same. Option 3 is correct. In this question, the variation of particle momentum and the de-Broglie wavelength, we know the formula here is de-Broglie wavelength is given by h upon p or h upon mv. So h is constant, lambda is inversely proportional to p. It means the graph here between p and lambda is inversely proportional graph like this. So option 4 is correct. A metallic surface radiated by monochromatic light of frequency mu1, stopping voltage V1. If the light of frequency nu2, we have to find the stopping voltage. Now we know the photoelectric equation H nu equal to work function plus stopping voltage V0. Putting all the values here, H nu2, work function plus E V02. H nu1, work function, it is same for the metallic surface, E V01. If we subtract from this equation, it will be cancelled out. Now H nu2 minus nu1 equal to E V02 minus V01 is given as V1. So we can easily find H upon E nu2 minus nu1. ये नीचे चला गया, ये उधर चला जाएगा. So plus V1. This is what V02. So here option 2 correct. In a photoelectric experiment, stopping potential for the incidenting light of wavelength 4000 angstrom is 2 volt. If the wavelength is changed to 3000 angstrom stopping voltage. We have to find. Here we know hc by lambda is the energy of the incidenting photon, and this is the work function, and V naught is the stopping voltage. In these values here, hc by lambda here is 4000 angstrom. Is the work function plus E into 2. 2 is the stopping voltage given. Now hc upon 3000 angstrom, work function remains the same. E into now V, we have to find out this value unknown, stopping voltage. Because there is no change in the work function remains the same here for the same material. Hc also same, E is also same. So if we reduce this wavelength, then energy increases. So stopping voltage must increase. Means stopping voltage should be more than the previous case, to more than 2 volts. It means option 4 is correct. The de-Broglie wavelength associated with a ball of mass 150 gram at a speed of 30 meter per second. So we know the de-Broglie wavelength is given by h upon mv. Putting the values here, 6.63 into 10 power minus 34, Planck constant, mass 150 gram, converting into kg, and speed 30. If we solve it here, we are getting roughly is 1.47 into 10 power minus 34. After calculation, it comes here. So option 1 is correct. Hello. In this question, a particle of mass 4m mass at rest, it decays into two particles of masses small m and 3m. It breaks into two parts, m and 3m, having non-zero velocities. Now we have to find out the ratio of de-Broglie wavelength of particle 1 and 2. Now we know the formula here of de-Broglie wavelength is given by h upon mv or p. It breaks up into two parts. Anyway, initially, for a mass is at rest, it converting into one m mass and other is small m mass with velocity, suppose 1 and 2. Mass is m1, m2 and this. So P is constant, conservation law of linear momentum. So we have to find out the ratio of the de-Broglie wavelength. P remains the same. It means lambda 1 will be h upon m1 v1 is equal to lambda 2 h upon m2 v2, but m2 v2 and m1 v1 is same, so lambda will be the same and ratio will be the 1:1. Means option 4 is correct. Hello, in this question, work function is 3 electron volt, and to emit the photoelectron energy, kinetic energy is equal to 2 electron volt. Using the equation hc by lambda equal to work function plus kinetic energy, both are in electron volt, 3 plus 2. So 5 electron volt. It means lambda can be found as upon 5 electron volt को जूल में चेंज कर लिया, 1.6 in 10 power minus 19, h Planck constant 6.63 into 10 power minus 34, is 3 into 10 power 8 upon will become 8 10 power minus 19, solve करके 24 0.75 angstrom and nearly 2486 angstrom. So option 4 is correct. The wavelength of the matter wave is independent of. As per the de-Broglie wavelength, we know energy is given by mc square or hc by lambda. So lambda is given by h upon m into c. Here there is no charge. Velocity, it must move. When v, particle is moving with velocity v, the metal or any body particle is producing the wave. Here the body charge होना जरूरी नहीं. So even neutral body, if it is moving, produces the wave. That is called the matter wave. The charge is not necessary here. Means option 4 is correct. Lambda does not depend on charge.